So let us talk about some of the issues with mission 2. So first of all, for problem 12, I think you guys are pretty much right, but I would urge you to look at my solution because like part B of that, there was a thing that neither of you did. So like one of you just didn't notice that there's a part B to the problem. And then here, I'll let you hold on to this here.
You can just take the first page out.
Just take the first page. Well, I don't want to. Well, is that what you want me to do?
Yeah.
All right, well, for now. So I just want to talk about this one briefly because there's an idea to use here that I didn't ever share with you guys, but in trigonometry, there's a place where we solve, well, not trigonometry, pre-calculus. Let me just show you an idea here that might make solving problems like this easier. If you like it, you like it. If you don't, it's fine, whatever. But this is 1/2 e to the z minus e to the minus z equal to I, right? Which is e to the z minus e to the minus z equal to 2i, right? And then if you multiply this by e to the z, what do you get? You get e to the z squared minus 1 equals 2i e to the z, right? Oh, is there 1 there? Yeah. Great. So if we let w equal e to the z, then what do we have? We've got w squared minus 2iw, right? Minus 1 equal to 0. So we can change this to a quadratic equation in w like this. See that? And then, now of course, you guys did it more like I was showing you in class, and that's fine. But I think each one of you got the solution a little bit wrong from the one in class, just because, like, Audric, yours was right, but then at the end, you found y was equal to something, and you put it in for x instead. Like, you should have multiplied. Since it's the y part, your solution would have been like I times what you found. Yeah? So, like, you were close, but not quite. Anyway, so this is, can you factor this? Well, this is w plus I squared, right? Yeah, I think it's w plus I squared, isn't it? You multiply that out, what you got? Minus I, rather, right? See that? Do you guys agree? So w minus I squared gives me w squared minus 2iw plus I squared, but I squared is minus 1. So this just straight up factors, right? Now you might say, oh, well, you got lucky, right? Because that's because you got an I here, it factored, right? But if it didn't, anything else you could put there, you could still do the quadratic formula, basically, right, to factor. Or you could complete the square, you know. So I do think that this calculation is more general than this specific case. And I don't know, maybe it's a better way to calculate this. I don't know. You see what you think. So this means that w is equal to I, right? But this means that e to the z is equal to I, right? And that means that z is an element of the little log of I. Because we can take little log of both sides of the equation, so to speak. But keep in mind that that means that z is an element of the set of values log I. What is log I? Well, log I is natural log of the modulus of I plus, I arg I plus, 2 pi iz, so to speak. And so this is log of 1, which is 0. And the argument of I, pi over 2, right? So what we're looking at is pi over 2, I times pi over 2, plus 2 pi I z. Or if you want to write it as a set, it's the set pi over 2 plus 2 pi k times I, such that k is an integer. So this is just a different way to go about it. I mean, this is certainly, I was not expecting you to do this, right? Because I was guiding you in a different direction in my, hints for this problem. But this is what the solution is, and I wanted to explain to you where this came from. It's a different way of doing the problem, okay? Anyway, let me talk just a bit about problem 16. So here you had, you're looking at H as the half plane, and you're supposed to give a sketch to show that 1 plus I is an interior point of H. So the half plane H, what was it? It was Z in the complexes such that the imaginary part of Z is greater than 0, right? So a picture of this is, the real axis not included, right? And then here's your imaginary axis, right? And I said, give me a picture which shows you why 1 plus I is an interior point. So 1 plus I is like right here, right? Roughly speaking. And so what's the picture I was looking for? The picture I was looking for is, what does it mean for something to be an interior point, right? That's the question. So to be an interior point means that there's an open disk, right, around that point, which is inside the set. So the set here is everything above, like everything up here, right? This is the set. This is what I've called H here. So I can't remember if one of you had it, one of you didn't, but anyway, you just need to point out that there's an open disk here, right? And this would be, what could I make epsilon?
I think I set it between
1 and 0. Well, but pick a specific one. Convince me that it's there. So how about a half, yeah? So d of 1/2 of 1 plus I, that is the disk of radius 1/2, right? Centered at 1 plus I, where the edge is not included, right? So I've tried to illustrate that with the yellow dotted, right? And as you can see, this is what? A subset of H, right? So thus, 1 plus I is interior point. So that's all you had to do there. This is the definition of interior point, that there exists a open disk. You don't have to, the question, I mean, it's good, Audric, that you're trying to describe to me all possible open disks, but we don't have to do so much. All you need to do is prove to me that there is a specific open disk for that point to prove it's an interior point. Now, where this gets more complicated, of course, is like in your next homework or in quiz 3, where you have the task of showing something, a set is open, right? Then you have to pick an arbitrary point and give an argument for there existing an open disk around that. We'll talk about that in a bit. But I wanted to finish mission 2 here before I get back to that. Problem 17. Problem 17, you guys are making your life too complicated. You need to embrace, so here we had an equals z to the n, right? An equals z to the n. And my point to you would be, we can write this as the modulus of z times e to the I theta, right? There's a polar presentation of any complex number. And what happens when you raise that to the n power? Well, you get modulus of z to the n, right? E to the I n theta. And so as you think about limits as n goes to infinity of a sub n, this observation is key, right? Pretty much everything in my solution flows from this observation. See, because you remember how it works for, if we could write this as, if z is r e to the I theta, maybe that helps, then a sub n is equal to r to the n e to the I n theta. And basic real analysis, calc 2 really, not even real analysis, limit as n goes to infinity of a real number to the n power is what? Here. So here, by the way, 0 is less than or equal to r is, right? I mean, r is non-negative here. So, yeah, it converges to 0 if 0 is less than or equal to r is less than 1. It's 1 if r is equal to 1. And it's infinity if r is greater than 1. That's what happens. Those things can be proved using the bounded monotonic sequence theorem, but you know what? Leave that for real analysis, yeah? Or honors calc 2, whatever floats your boat. So everything I said in my solution to problem 17 stems from just this basic observation, like this is the way to look at the formula, all right? And that's just a more general piece of advice I have for you guys. If you're trying to understand a complex number to a power, maybe polar coordinates are something you should look at in terms of gaining insight as to what's happening. You know, because if I look at the formulas for z squared, for z cubed, for z to the fourth in terms of x and y, I mean, I can calculate those, but it's easier to gain direct geometric intuition for what's going on in this way. So essentially all that's happening is that if your z, so I can draw a picture, right? So if your z, if z is in here, right? If it's inside the disk of radius 1, what's going to happen? A sub n is going to converge. See, because what you have is, you know, the limit as n goes to infinity of, you know, modulus of z to the n times e to the I n theta equals to 0, since this modulus of z to the n goes to 0. If you like, you could take the absolute value of it, show that the absolute value of the sequence goes to 0. Consequently, the sequence goes to 0. That was another problem I think you had in here. Well, I didn't give you the sequence version. Problem 19 was like that, but there is a problem 19. There's a version of problem 19 for sequences, by the way. So problem 19, also true for sequential limits. In other words, if you have the limit as n goes to infinity of like the absolute value of a sub n is equal to 0, that implies that the limit as n goes to infinity of a sub n is equal to 0. So we can apply that theorem, if you like, to solve the limit and show it converges to 0 inside the unit disk. On the unit disk, 1, if you have z equals to 1, it converges to 1. Otherwise, as n goes to infinity, if you think about what's happening, your point's just going round and round and around the unit circle. It never stops. And if your point is outside the unit circle, as n goes to infinity, you have that modulus of z to the n blowing up. So the limit doesn't exist. Anyway, just wanted to share that way of thinking with you for problem 17. Problem 18 I talked to you guys about. I think if you look at my solution, you'll see that what I talked through with you, Jade, is like more sophisticated than my solution. The solution I have is like a little bit sketchier. That kind of problem, if I was to put that kind of problem in the test, really I'm just looking for like a picture and an intuitive kind of solution. But in all likelihood, that one's not on the test, to be honest with you guys. Because we only have so much time, right? And much more important things are like Cauchy-Riemann equations and, you know, other things. Problem 20, there were some problems with problem 20. Like, you guys are not following my instructions. Well, some of you might have followed some of my instructions some of the time, but let's talk about problem 20 here, because it doesn't have to be complicated. So problem 20, you had f of z, was it 1 over z squared? Right? Is that right, or is it 1 over z? I can't remember. I've walked away from it. 1 over z squared, right. So first of all, you're supposed to calculate the derivative, let's say f prime of a, with the difference quotient, right? And so you got two options. You can either do the h goes to 0 thing, f prime of z, I guess. Fine. So I'll do it like this. So that would be the limit as h goes to 0 of 1 over z plus h squared minus 1 over z squared divided by h, right? This is the limit of the difference quotient. Like, this is the same as Calc 1, right? Just with the function, with z's instead of x's, but... and, okay, so this is limit as h goes to 0. Let me try to do the math right quick here, h. So you got yourself a z squared minus z squared plus 2zh plus h squared, all divided by z plus h squared times z squared. I made a common denominator. The z squareds be canceling. Got an h on everything that's left. So that reduces down to minus 2z plus h divided by z plus h squared, z squared. And then at that point, you can plug in the limit. You got minus 2z over z squared, z squared. In other words, minus 2 over z cubed, which is, of course, not surprising because that's the power rule, right? My point to you is this could very well have been a Calculus 1 problem, like on the first test in Calculus 1, right? Maybe the second test, depending on how your teacher parsed things, but this is a definition of the derivative problem. That was part A. Now, part B, I asked you to use the theorem of Carathéodory. And so to do the theorem of Carathéodory, what you want to do is to look at f of z minus f of a. And usually when you do that, you'll be able to see what the quotient function should be. All right, so if when I do that, this is 1 over z squared minus 1 over a squared. And so if I make a common denominator here, I get, a squared minus z squared over a squared z squared. Or this is minus z plus a divided by a squared z squared times z minus a. So this is the game. Look at f of z minus f of a and factor out z minus a from that. Whatever you're left with as a cofactor to z minus a will be the quotient function for the theorem of Carathéodory. So this identity suggests to me that we should define phi of z as such. This is my phi of z. Right? So this equation is already satisfying criteria 2, I believe it was, of the theorem of Carathéodory, namely that it satisfies the condition, f of z minus f of a is phi of z times z minus a. And what else do I need? I need that phi of z is continuous at a, right? Note the limit as z goes to a of phi of z, what is it equal to? See, there's no indeterminacy, right? Like, you can just plug in a into that. We get minus 2a over a to the 4th, which, of course, is minus 2 over a cubed. And then by the theorem of Carathéodory, this is equal to f prime of a. So the algebra is related, right? Any way you slice it, you're going to have that, like, making a common denominator calculation is in there. And of course, it would look even more similar if I'd used, instead of an h goes to 0 approach in the first one, if I'd used like limit as z goes to a to calculate f prime of a, because that's the other way we can do the difference quotient, right? But since I did f prime of z, I didn't want to do the f prime of z. I don't do you do like z goes to z. That what? No. So you want to do if I'm calculating f prime of z, h goes to 0 is the way to do it. F prime of a, on the other hand, if I was to calculate f prime of a, then I could have taken this approach, right? I'm just saying you got these two different competing notations for how to calculate the derivative. The trouble with the f prime of a thing is if you want f prime of z, after you do the calculation for a, then you have to replace a with z after you're done with the limit. You know? So just like computationally, it's kind of a little unsatisfying. All right, so those are my list of I don't know what you want to say. These are the things in the solution which I think that I should tell you. The other thing was problem 19. Both of you were thinking about the limit at least one point or another as being a limit as h goes to 0 can be a limit from the right and a limit from the left. But the thing is, h is a complex number. As h goes to 0, that's a two-dimensional limit. So there are infinitely many different paths to 0. We have to take like an epsilon delta approach in that problem. So there's not much to do there, but I'll let you look at the solution. So mission 3, let's talk about mission 3. So, is there a particular one you guys want me to talk about?
Can you hand me back mine? This is my mission 3. I think 26 and 27 part A.
26 and 27 part A. So, so with problem 26, let's see here, you've got f is holomorphic on C, right?
Yeah.
And what else are we given? F. Yeah, f is equal to u plus iv. And what else we're given? We're given ux. Yeah. Where do we go? X squared plus y, right? On C. So of course, you could also write this just ux equals to that if you want, but okay, so I say, is this possible? If so, find all f of z for which this partial derivative is given.
I mean, I started by like finding u.
Started by finding u.
Yeah, because we know that's the first partial derivative of u.
Yeah, I guess you could do that. So this means
We just got 1/3 x cubed plus yx plus c.
so you got u is equal to 1/3 x cubed plus xy plus c, which is a function of what? Y. All right. Sure, you can do that.
And so, like, from the other problem, like, for 24, like, you gave us a harmonic conjugate.
Well, 24 was the sharp bound thing, but
I mean, 25, sorry.
25. Mm-hmm.
And so I was thinking, like, you kind of approach it like that. But, like, I kind of ran into trouble because I was like, well, that doesn't look like a conjugate.
Well, I don't. You're trying to see it as the real component of a complex function, you're saying, or?
Yeah.
Oh,
that is
yeah.
a real component of a complex function.
Right. The question is what f of z would make that happen. So what I would do in this kind of problem, because it feels to me like when I read this problem, I'm like, this is probably not true. That would make the problem interesting, right? Okay, so what do we have to satisfy? The CR equations, right? So we need ux equal to vy, right? And we also need uy minus vx. I don't know if that's going to help us or not here. So So this would be equal to what? This would be equal to,
We're going to UI. Try to find UI.
yeah, this would have to be equal to, oh, I'm sorry. So this would say that, like, Vy has to be equal to Ux, right? Has to,
We found source.
well, we already know that's x squared plus y that was given, yeah.
Yeah. So if we're looking for UI, that would give us like, that'd give us C prime Y.
So yeah, so v would be what, 1/2 y squared, right? Plus xy plus like c2 of x, right? Well, if you can integrate with respect to x, I can integrate with respect to y.
Yeah, but I'm saying,
Does this help?
well, I'm saying that we know UI, right? So why don't we take the derivative of u with respect to y to find Vx? So we found u.
Okay. I mean, you're saying find uy then?
Yeah.
Okay, sure. Uy is what?
I got C prime Y.
So x plus dc, dc dy, yeah? All right, and that's equal to what?
Vx.
Minus vx. Well, there's v. What's minus vx?
Minus Vx. That would be,
So I guess, first of all, here, I'll just write down vx. Vx would be what? Y plus dc2 dx, right? So this is equal to minus vx, which is equal to minus y plus dc2 dx.
which is, you got two differentiations for different functions.
So the only way this can be true, right?
And you actually have alternate y too.
So this is the only function of x on that side, right?
Yeah.
So it has to be matching this.
Yeah.
And this is the function of of y on that side, so it has to be matching that up to like a constant.
Yeah. So you get x minus y and x minus y.
So it looks to me like dc dy equals minus y, and dc2 dx equals to x. So c is equal to minus 1/2 y squared, and c2 1/2 x squared.
Now we have a full equation for u plus iv. We find v from what we have.
Okay. So let's see here. U is equal to 1/3 x cubed plus xy plus, let's see here, minus 1/2 y squared. And v, of course we can add a constant, right? But v is equal to, what was it? 1/2 y squared plus xy plus 1/2 x squared, yeah? Yeah, I don't think that's, well, I guess now you can check is, let's see here.
Well, you get, it has an I attached to it.
See, guys, anyway, the point is, you can do all this, and it may or may not be. I think you can deceive yourself into thinking you have an answer here, but let me erase all this and show you a simpler path. Okay? So, these are good calculations. It's just, there's something that tells us these are doomed to failure from the outset. Let me show you what. I was hoping we would find our way to a contradiction in those calculations, but it just didn't pop out. That's why I kept doing them. Usually the contradiction will pop out. Maybe I just didn't, maybe it was right in front of us and I just didn't see it. But what do we know about holomorphic functions? What is one of the things they are? Holomorphic implies harmonic. So this implies f equals to u plus iv with harmonic u and v, right? Which means what? That means uxx plus uyy equal to 0, and vxx plus vyy equal to 0. What is uxx? 2x. What is uyy? Oh, we don't know.
It was 1/3. It was
Curses.
It was 1/3. No, it was 1/3 x cubed.
Yeah, my bad.
Plus xy plus cy.
Okay, so yeah, I've erased too much. We had u is equal to 1/3 x cubed plus xy
Plus c of y.
c of y, yeah. So what's uyy?
Well, uy is going to be y plus c prime y.
Mm-hmm.
And so uyy would be c prime prime y. 1 plus 1.
Yeah.
No.
Well, the y derivative makes this and that go to 0.
Yeah, c prime prime.
So yeah, c prime prime. Or d squared c dy squared, right? So then you're left with a question. Can we have uxx plus uyy, which is equal to 2x plus d squared c dy squared? Can this be equal to 0?
No, because we have a function of y.
No, exactly. So this, if you like, this, if you just want proof positive, take the partial derivative with respect to x of this equation, right? And you get partial x of uxx plus uyy is 2. But if uxx plus uyy equal to 0, we wouldn't have that being 2, would we? We would have it being 0. Another way to see this is if you have an equation where you have a function of x plus a function of y is equal to 0, the only way that can go is if both the function of x and the function of y are the constant function. But 2x is not the constant function in x, so that's impossible. Anyway, so no, u is not harmonic, therefore what?
It doesn't side with the holomorphic.
Harmonic, which implies that there does not exist v such that u plus iv equal to f holomorphic on D. Because if there was, it would imply that it's harmonic. Both of the component functions are harmonic, but the given function u is not harmonic, so we're out of luck. So what are the different characterizations we've had of a holomorphic function? Of course, the first is the definition, right? That the complex derivative exists on an open set around the point, right? And then what are the consequences of that? Well, the component functions have to be harmonic, right, is one thing. More interestingly, they have to satisfy the Cauchy-Riemann equations, right? What else? They have to give us a conformal map, right? So these are different ways of testing for complex differentiability at a point in some open set around the point. Namely, again, we call that holomorphic. Let's see here. Oh, that one's not bad. You can just look at the solution for that one. 27. Again, it's just if it's holomorphic, you have the Cauchy-Riemann equations. So like the length of the gradient of u is the length of the vector ux, uy, using like Calc 3 notation. So that's the square root of ux squared plus uy squared. But remember that uy is minus vx, right?
Yeah.
So you got ux squared plus minus vx squared. But that's exactly the length of ux plus ivx, which, by the way, is the modulus of f prime of z. And I think I got to put in a naught because that problem was at naught.
Yeah.
And a similar calculation goes through the gradient of v. Now, let's talk about, let me shift over to the quiz. I think those are my main comments for the, the problem 30 is a little bit of a, it's just kind of definition chasing. The problem's not actually that hard, but I know it'll seem unfamiliar to you guys, for sure. So, let's see here. So do you guys have any questions about quiz 1? So quiz 1 is due Wednesday.
When we're showing an open set, like how I did, I just drew a picture.
So let me make your life a little bit easier. I'm gonna for problem 8, you can use limit laws. All right. And so what I mean is to show it's continuous on C. You want to show the limit. Oh man, what the world? Limit as z goes to z naught, right? Of f of z. So limit of x plus iy goes to x naught plus iy naught of, it was x plus y plus iy squared. So in the solution that you'll read for quiz 1, I will give you the epsilon delta proof for this, I believe. All right. But I don't feel like I've done enough of that in here to put that on your test. All right. I want you to know the epsilon delta definition of the limit, but to actually pursue the epsilonics for this problem it's kind of a little bit involved. But we do know limit laws. So this is like x naught plus y naught plus iy naught squared, which of course is f of z naught. So there you go. There's the proof. I will you can give me back this proof to show that the function's continuous on z naught. Right. So what was your question, Audric?
Problem 10.
Oh yes, problem 10. Let's talk about that.
And I just drew a picture because like you pretty much get this straight up and down line things.
Mm-hmm.
And I'm like, well, just gotta show that's an open set between 1 and 2. And so if I remember right, like you do the same thing. You pick a point as close as you like to the line, and you can show there's a disk around it.
All right. So let's talk through this. Yeah, that's a good idea. So there's it's a vertical strip, right? Very good. Fuzzy edges. So like intuitively speaking, if we're not burdened with the task of proving that it's an open set, we're already like, well, it's an open set. It's got fuzzy edges, right? But suppose we want to be more rigorous. Then, okay, so the center line is where, like here, right? 1.5.
Yeah.
X equal to 1.5. Fine. Just saying. So you want to pick a point, right? Like here. And then you're going to draw a disk around it. Okay.
What I was saying is you can pick an arbitrary point as closest to the line you like.
Which line? There's 2 lines.
Either one.
So tell me what epsilon is.
For any line.
So like given if
The
z,
distance
so
between the point and the line.
so let's say z in the complex is such that 1 is less than the real part of z. Let's say x. Z equals x plus iy, right?
Yeah.
So you've got 1 less than x less than 2, right?
Yeah, I just said pick an x like as close as you like to the 1 line or the 2 line.
No, but you have to prove it's open, you have to pick an arbitrary point in here and tell me the radius.
So yeah, you can just take the distance between the point and the closest line and find it.
Distance between the point and the closest. Let epsilon equal the distance between z and closest x equals 2 or x equals 1, right?
Yeah. And there's always, like, we know that.
That's good. What does that mean? Can you give me a formula for that? Minimum of what?
Like the formula between the point and the line.
Minimum of,
Epsilon.
well, x is the fixed thing here, right? So minimum of what? Let's put some knots on this just to be more annoying. Z sub naught, z sub naught, x sub naught, y sub naught, x sub naught. Okay. Z sub naught, x sub naught. Oops, excuse me. X equal to 2 or x equal to 1.
Like the minimum, the epsilon minimum is, would be 2? Like, are we talking about like the...
In terms of x naught, minimum of something. I'll get you started. It's a minimum of the absolute value of 2 minus x naught,
Plus x naught?
comma,
Oh, any y. Y.
no y. Y's got nothing to do with it. It's all about x.
Oh, that's the minimum. And then 1, and then x minus 1.
Yeah, or of course, if you like, you could do, x naught minus 2, x naught minus 1,
Yeah.
right?
Yeah, I got you. Mm-hmm.
That's your epsilon,
Yeah.
right? So your claim is that the disk of radius epsilon centered at z naught is a subset of whatever I've called the set. What do I give it a name? S. I called it S, right?
Big
Big S, yeah. That's the claim, right?
Yeah.
So if we're going to give a rigorous proof, what do we have to do to show one thing's a subset of another? We have to pick an element of the alleged subset and show that it's in the superset, right? So we should let z, let's say equal to x plus iy, be an element of the disk of radius epsilon centered at z naught, where epsilon we've defined according to that right there.
Yeah, but z can't just be any x plus iy.
Z has to be any x plus iy in that disk.
In that disk, okay, yeah.
Yeah. So what does this tell us? This tells us that the modulus of z minus z naught
Oh, yeah.
is less than epsilon, right?
Yeah.
But epsilon, so this, right, is what? Thus, the modulus of x minus x naught, which is less than or equal to the modulus of z minus z naught, right, is less than epsilon. See, because the difference between the real parts has to be less than or equal to the difference between the whole complex number, right? This goes back to a basic principle, which is that the length of a particular component of a complex number has to be smaller than or equal to the length of the whole complex number. Right? So the length of the real part of z minus z naught, which by the way is x minus x naught, has to be less than or equal to z minus z naught. But we know that's less than epsilon by construction, right? So then what? So this gives you that, the absolute value of x minus x naught is less than the minimum of absolute value of x naught minus 2, comma, x naught minus 1. Now there are two cases, right? There are two cases to think about. If the minimum of x naught minus 2, comma, x naught minus 1 is equal to x naught minus 2, then what? Absolute value of x minus x naught is less than absolute value of x naught minus 2. how can we, what does that mean? Now, I should mention that we know that this is equal to 2 minus x naught, since x naught plus I y naught was an element of S. That was assumed at the outset. I shouldn't forget about that. That matters. Otherwise, I was about to get really lost.
Okay.
If not for that.
So the minimum equal to then,
Because 2 is beyond all of the x naughts, right? And so this gives us minus 2 minus x naught is less than x minus x naught is less than 2 minus x naught, because when we have an absolute value less than something, it unwraps into the compound inequality like so.
Yeah.
Thank you, Math 101. Okay, with Math 101, we do not put x naughts and stuff in there, right? But
You don't have to have the less than or equal to there? No, you took it to on.
yeah. And so what happens now? We want to find just so add x naught across this, right?
Yeah.
So you've got
minus 2 or less than greater than x.
So we got 2x naught minus 2, right?
Yeah.
Less than x, less than what? 2,
yeah,
right?
x naught is 2.
Got this in 2, right?
We have x naught less than x. Add a 2, give you 0.
So I think if we, so here is where the fact that it was the minimum equal to this, so we know what? We know that, x naught minus 1 has to be greater than 2 minus x naught, right?
Yeah.
Which tells us that 2x naught has to be greater than 3, apparently. So this is what?
Yeah.
This is then less than, excuse me, well, curses. So 2x naught minus 2.
No, that makes sense, because that means if it's greater than, but, yeah, wait, do we have an upper bound on x naught?
2.
Yeah, and on x naught, but it has to be greater than 3.
I mean, so I don't know. I'm sorry. This is getting messy, but the point is that this is, this is x naught is greater than 1.5, right?
Yeah.
The two cases should be, like if I sort through this, if I sort through the inequalities and don't make a mess of it, we've got 1.5 in the middle, we've got 2 over here, we got 1 over here. So either x naught's in here, right, or x naught's in here.
Yeah.
And we're in the case where this is the smaller one, which means that the point is to the right. And
I'm just going to say C is complete. Therefore, like you take an arbitrary line, there's always points smaller and smaller.
oh, well, that's true, but
You can, like,
all right. So
there's always an R defined that you can make a radius epsilon disk out of as close as you like to 2.
oh, curses.
You need the quiz.
So yeah, we're just about out of time here. So my point to you is, if we sort through this, and I always get stuck on the details here, but I'm trying to say is, the full and annoying proof goes through all these kinds of like unwrapping the inequalities things, right? But I will give you full credit if you at least give me like a picture, tells me how you're going to choose the epsilon, and tells me how each different case in the picture is dealt with by your choice, right? So there's 2 choices, right? If you're to the right, you chose epsilon to be the smallest distance to the edge from the center, and so therefore that means the disk fits within the right band. And then the other picture to draw is, if the point's over here, then you choose the radius for your disk to be the distance from the center to the left edge. So, but anyway, when you look at the solution to the quiz, I have the complete, like, case-wise, blah, 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 but.
I might try to go for
Any other questions about quiz? Do you guys think you're good on the fractional linear stuff?
Yeah, I think so.
Okay.
Two might give me some problems.
Oh, one other thing, this will take just a second. The cos squared plus sin squared one, check this out. Cosine squared z plus sine squared z is equal to f of z, right? Check this out. This is a function. No, I'm doing cosine, similar but different problem. Cosine squared plus sine squared, function on complex numbers. Differentiate, what do you get? F prime of z, work it out, chain rule, minus 2 cosine z sine z, plus 2 sine z, cosine z sine z. The derivative is 0. This is 0 on c, right? The complex numbers, by the way, are connected. We had a theorem. If the derivative of a holomorphic function is 0 on a connected set, it means the function is constant on the connected set. So f of 0 is what? Cosine squared of 0 plus sine squared of 0, right? Which is 1. So therefore, cosine squared z plus sine squared z is equal to 1 on c. So don't make that problem harder than it needs to be. You can do a similar argument for cosh and sinh. And this is a super nice way of proving identities for complex numbers. We can use this trick. Anyway, I shut up for today.